So in this section, we're going to talk about implicit differentiations. So all the functions of consideration so far are written explicitly in terms of x and y, or in terms of t, or in terms of u and v. Now, there's a lot of situations where the functions cannot be expressed explicitly in terms of independent variable. That is, the function are written implicitly in terms of x and y. In those cases, when you want to find the derivative of the functions, you have to apply something called implicit differentiations. Now, suppose the function z equal to f of xy defines y implicitly as a function of y equal to g of x via the equations f of xy equal to 0. Then to find the derivative of dy dx, you have to take negative of partial f partial x over partial f partial y. And later on, I'm going to derive this formula, so bear with me here and just let's accept this formula for the time being. So because we arrive as a fractions here, we don't want the denominator to be equal to 0, so we need to impose the conditions that partial f partial y has to be different from 0. So let's jump into the derivations. So consider the following equations of f of x comma y of x. And to find dy dx, we treat x as an independent variable and differentiate both sides of the equation with respect to x. The derivative of the right-hand side is 0 for obvious reason, right? So because the derivative of a constant is equal to 0. Now on the left-hand side, we're going to apply chain rule that we just learned. And we're going to arrive at partial f partial x times dx plus partial f partial y times dy dx, and this is equal to 0. So the left-hand side is because we apply the chain rule for function of one variable. In this case, the variable or independent variable is x by the assumption. Okay, so that's why you get partial f partial x, because f is the function of two variables x and y, therefore the partial derivatives. You multiply with dx because the independent variable in this case x only. And you do the same for the second part here, partial f partial y times dy dx, again the independent variable in this case x only. So the derivative of x with respect to x is equal to 1, therefore you have partial f partial x plus partial f partial y times dy dx, and that is equal to 0. From here you're going to solve for dy dx, and easily we can see that dy dx is equal to negative of partial f partial x divided by partial f partial y. And because you arrive at the fractions, you don't want the denominator to be equal to 0, therefore you impose the conditions that partial f partial y has to be different from 0. And that is the result for the formula that we get up here. Now I'm going to give you another formula in the case of functions of 3 variables. So if you have the equations of f of x, y, and z equal to 0, define z implicitly as a differentiable function of x and y, then you're going to get that partial z partial x is equal to negative of partial f partial x divided by partial f partial z, given that partial f partial z has to be different from 0. And you have partial z partial y is equal to negative of partial f partial y divided by partial f partial z, given that partial f partial z is different from 0. And we can have the very similar derivations for these two formulas if we follow the same instructions from these derivations. Okay, so I'm going to apply this formula to some example here. So in example 6, you want to find partial z partial x and partial z partial y if z is defined implicitly as a function of x and y by the following equations. So there are two ways to approach this problem. The first one, which we're going to use the formula given to us on the last page. The second approach is that we're going to follow the implicit differentiation technique that we learned in the single variable calculus. All right. Now I'm going to show you both ways how to find the derivative of the functions in this case. So for the first method, I'm using the formula partial z partial x is equal to negative of partial f partial x divided by partial f partial z, and you have partial z partial y equal to negative of partial f partial y divided by partial f partial z. Given that f is equal to x cubed plus y cubed plus z cubed plus 6xyz minus 1. And this is equal to 0. So we move everything to one side of the equations. Now to find partial z, partial x, and partial z, partial y, we need to derive the formula for partial f, partial x, and partial f, partial z, and partial f, partial y. So to get partial f, partial x, you're going to do partial x of x cubed plus y cubed plus z cubed plus 6xyz minus 1. And here, when you take partial derivative of the function with respect to x, you're going to treat y and z as constant. Okay, and here you're going to get 3x squared plus 0 plus 0 plus 6yz plus 0, because the derivative of negative 1 is 0. And you get this to be 3x squared plus 6yz. Now for partial f, partial y, you do partial y of x cubed plus y cubed plus z cubed plus 6xyz minus 1. And in this context, x and z are constant. So you get this to be 0 plus 3y squared plus 0 plus 6xz plus 0. And you simplify the result and you get 3y squared plus 6xz. And for partial f, partial z, you do partial z of x cubed plus y cubed plus z cubed plus 6xyz minus 1. So in this context, x and y are constant. And you get 0 plus 0 plus 3z squared plus 6xy plus 0. And you simplify the result, you get 3z squared plus 6xy. Now you have all the information that you need. Plug this information into our formula to get partial z, partial x, which is equal to partial f, partial x divided by partial f, partial z. So this is equal to negative of 3x squared plus 6yz divided by 3z squared plus 6xy. Similarly, you have partial z, partial y is equal to negative of partial f, partial y divided by partial f, partial z. So here you get negative of 3y squared plus 6xz divided by 3z squared plus 6xy. And that's how you obtain the partial derivative of functions with respect to an independent variable if the function is written implicitly in terms of the independent variables. All right, so that's one method that we can use to actually obtain the implicit differentiations. There's another method that you can do that is very similar to the technique that we approach in single variable calculus, and I'm going to show that in the next example. So in this example, you want to calculate partial z, partial x, and partial z, partial y, given the equations of x squared times e to the y minus y times z times e to the x equal to 0. So I'm going to start out with the equations, and to find partial z, partial x, what I'm going to do is I'm going to take partial derivative with respect to x on both sides of the equations. So I'm going to start with x squared e to the y minus yz e to the x equal to 0. And I'm going to take partial derivative with respect to x on both sides of the equations. And on the right hand side, obviously, that's going to be equal to 0 because you take partial derivative of constant. And on the left hand side, you're going to take partial derivative of the functions with respect to x. So y in this context will be treated as a constant. So z in this case is defined implicitly as a function of x and y. So when you take the partial derivative, the partial z, partial x will remain. So that is the partial derivative of x squared times e to the y is going to be 2x e to the y minus partial x of yz e to the x equal to 0. So I write partial x in this case because, again, z is a function of x and y and it's not a constant. So technically you need to apply product rule for this calculations. So here you got 2x e to the y minus y times partial z, partial x times e to the x plus z times e to the x. So here what I did is I applied product rule for z times e to the x. So the derivative of the first function times the second plus the first function times the derivative of the second function. And that is equal to 0. Now at this point you can solve for partial z, partial x. So you have 2x times e to the y minus y times e to the x times partial z, partial x minus yz times e to the x equal to 0. or you get y times e to the x times partial z partial x equal to 2x e to the y minus y z e to the x. And to get partial z partial x by itself, you're going to divide both sides for y e to the x, and you should get 2x times e to the y minus yz e to the x divided by y times e to the x. And that's how you get the answer of partial z partial x using the approach that we learned in single variable calculus. Now I'm going to perform a similar calculations, but for partial z partial y using the same approach that we're doing here. So again, we're going to start out with the equations of the form x squared e to the y minus y times z e to the x equal to 0. And I'm going to take partial derivative with respect to y on both sides of the equations. The right hand side is equal to 0. And the left hand side, I'm going to get x squared times e to the y. So in this case, x is the constant, and you take partial derivative of e to the y with respect to y, you get e to the y minus partial y of yz e to the x equal to 0. So again, x is treated as a constant, so e to the x is also a constant, but z is defined implicitly in terms of x and y. So therefore, technically, you need to apply product rule for these calculations. Here you get x squared e to the y minus e to the x times 1 times z plus y times partial z partial y equal to 0. So how did I get it? Again, I apply product rule for y times z. So derivative of the first function, which is 1, times the second, plus the first function times the derivative of the second function. And now at this point, you can solve for partial z partial y. That is x squared e to the y minus z times e to the x minus y times e to the x times partial z partial y equal to 0. And you can solve for partial z partial y from here. That is y times e to the x times partial z partial y equal to x squared e to the y minus z times e to the x. And to get partial z partial y by itself, you divide both sides for y times e to the x, and you get x squared e to the y minus z times e to the x divided by y times e to the x. And that's it for me for the implicit differentiations and overall the chain rule of functions of several variables. That's it for me. Please let me know if you have any questions. Thank you.